giving me an opportunity to attend this nice webinar. So, good morning, everyone, but now in Japan, midnight. So today I'd like to talk about the total thesis of Amphidiol 3 and structure-activity relationship study. Or so, okay. So Amphidiol 3, abbreviated as M3, was isolated from the dinoflagellate Amphidiol crevasse. This compound elicits potent antifungal activity and hemolytic activity. So, although the planar structure of M3 was reported determined in 1991, but it was downly tasked to determine the absolute configuration because of the limited availability from natural product from and also a number of strictogenic centers, around 70%, are located on the acyclic flexible carbon chain. So, however, in 1999, the absolute configuration of M3 was determined by Professor Murata and Tachibana and Matsumori group by extensive NMR analysis by using JBC method, modified moisture method, and degradation of natural product. So, however, the originally proposed structure was revised at C2 and C32 and to 36 and 38 and 51 by our study of M3, as shown here, the corresponding antipodal strictogenic centers, so that different from the originally proposed structure. So to confirm the absolute configuration revised in 2018, we emphasize the total thesis of M3 and comparison of the spectral data with those of the natural product. So we planned a highly convergent strategy for synthesizing M3, as shown here. So M3 would be synthesized through the assemblage of these three components via Suzuki-Miyawari coupling, the C bond formation at C29 and C30, provide Julia-Koshiansky olefination, the connection of the C bond at C52 and 53. So, however, in the strategy, it would be a daily task to assemble the largest segments shown here. So, and to construct the natural product, the molecular weight exceeds 1300, 1328. So because of the intriguing molecular structure and biological activities, a number of synthetic studies have been reported, as shown here, by famous professors shown here, by Professor Kossi, the next speaker, and by Professor Paquette, Rausch, and Professor Lichnowsky, Kremis, and also a number of synthetic studies have been reported. So this is the synthesis problem of the polyurol segment corresponding to the C1 to 29 section. The polymer molecule would be synthesized from this aldehyde and sulfone via Julia-Koshiansky olefination, and followed by regio and stereoselective dihydroxylation in the presence of these two olefins. So it's a key point of the synthesis of this segment. And compound 5 would be obtained from these two terminal olefins bear cross-metastasis reactions, and this compound will be synthesized from these three building blocks through the CC bond forming reaction and asymmetric reduction. This third form would be synthesized from this compound 12 from the 13 and 14 bear cross-metastasis reaction, followed by oxymical reaction and asymmetric cross-reaction. So, this is the scheme of the C24 to C29 section. Starting from alkyl production of a primary alcohol as TBTPS silane group and F-side opening with vanillin magnesium bromide in the process of copper iodide to give secondary alcohol, which was protected as TS ether. Then cross-metastasis reaction with alkyl rain and this terminal olefin was efficiently proceeded by the action of the Graff's catalyst to give alpha-beta unsaturated aldehyde, so which was subjected to the oxymical and acid formation reaction reported by Paul Evans by using the bismuth nitrate. This reaction works well to give this compound. Then reduction of the resulting aldehyde with soluble hydride and protection of the resulting primary alcohol as NAP ether. Then removal of the thyroid group with TBAF and oxidation of the primary alcohol gave aldehyde 19. Then this aldehyde was subjected to the asymmetric cross-reaction reported by Professor Raj using this Carlisle reagent to give this compound as a single isomer. Then removal of the acetyl group under the acidic conditions to give triol 20. And the triol was protected as TBS ethers. Then terminal olefin was converted to the terminal primary alcohol by hydroboration and oxidation sequence. Then this primary alcohol was converted to the sulfone, PT sulfone, via Mitsunobu reaction using this thiol. And the resulting sulfide was oxidized with MCPA to give this sulfone. So next we moved on to synthesis of the C5 to C20 section. So this is starting material, the terminal alkyne, which were treated with norambutylrithium to generate terminal lithium acetate, which was reacted with this vinyl amide to give compound iron 29. Then Noyori reduction using the same catalyst. The reaction proceeded well to give optically active proprietary alcohol. Then selective hydrogenation in the presence of the PMP was achieved by under the conditions reported by Sajiki using this catalyst. Then the alkyne was hydrogenated. Then protection of the secondary alcohol as TBS ether. And this one amide was treated with the alkaline lithium generated from this iodide by treating with normal butyrylithium. The addition of the vinyl lithium and amide for the alpha unsaturated ketone. The reduction of the ketone by using this color catalyst reported by Curie, CBS catalyst to give secondary alcohol, and the resulting alcohol was protected as TBS ether. So the one of the key reaction of the synthesis of polyol materials examined. The cross-metastasis reaction of terminal olefin 7 and terminal olefin 8 by using the 3 equivalent of 8. The cross-metastasis reaction proceeded smoothly by using a second-generation graph catalyst. The desired compound were obtained in 70% yield, and the easy ratio is 13 to 1 ratio. So after protection of the secondary alcohol, then PM group was removed with CDQ, and the resulting primary alcohol was oxidized by Parekh-Dehring oxidation to give aldehyde 5. Then Julia-Kroshansky origination of aldehyde 5 and sulfone by using a potassium hexamethyldiacid acid and at minus 78 degrees to room temperature. The designed compound was obtained in 86% yield. The mixture and to give the E isomer selectively in a 20 to 1 ratio. So next step is the crucial step of the present synthesis. Radio and stereoselective dihydroxylation was achieved by using sharpless asymmetric dihydroxylation conditions by using the monomeric ligand DHQ MEQ to give desired compound. The isomer ratio is 13 to 1 ratio. So this ratio and stereoselective dihydration was achieved in the presence of the other CC double here and here. So the production of the resulting secondary alcohol as TBS ether and removal of the PMB NAP group with DDQ, and the resulting primary alcohol was converted to the terminal olefin under the condition reported by Brickman and Nishizawa to give terminal olefin, the key segment compound 2. So then we moved on to the synthesis of the bis THP ring system corresponding to the C30 to C52 section. This compound would be obtained from the coupling of aldehyde and iodorphin via hydrogen lithium exchange reaction. And this aldehyde and this iodorphin would be derived from the enantiomeric tetrahydropowering system. Yeah, it's a very interesting structure, a completely enantiomeric form of the tetrahydropowering derivative. And the enantiomers would be derived from the enantiomers of these allylic alcohols, R41 and S41 respectively. So synthesis of the A ring and B ring as shown here. After protection of the secondary alcohol as TBS ether, cross-metastasis with the acrylate by using Grab's second general characteristic proceeded to give desired compound. Then the ester was reduced with divert, and the resulting primary alcohol was protected as benzene ether. The next reaction is ratio and stereoselective dihydroxylation in the presence of two olefinic parts. But the more reactive, this olefin was oxidized under the condition of sharpless asymmetric dihydroxylation, and the resulting diol was protected as acetate. The next reaction is the coupling, Suzuki-Mura coupling of iodide 15 and this pinacoreporane. The cross-coupling reaction proceeds nicely to give a coupling product. And after removal of the side group here, the allylic alcohol was subjected to the cask sharpless asymmetric epoxidation. And then resulting epoxide was after removal of the acetyl group, the epoxy alcohol was treated with PPTS. The 6-ender cyclization occurred to give the airing. So in an annual sequence, the bearing was also synthesized from this alcohol in 11 steps. Then the bearing was converted to the this aldehyde via Katsuki sharpless asymmetric epoxidation, and the resulting epoxy alcohol was subject to the pain rearrangement conditions to give the sulfide at the terminal position, and the resulting diol was protected at TBS ether. The next step is polymer rearrangement. The oxidation of the sulfide with MCBB giving sulfoxide, which was treated with trifluoroacetic anhydride. The resulting aldehyde was reduced with sodium borhydride. After production of the alcohol as PMB ether, the selective removal of the benzyl group at its conditions by using iron and nickel, and the resulting alcohol was oxidized to aldehyde. The airing was synthesized as shown here, corresponding to C31 to C42 section. The production of the diol as cyclopentadiol acetone, and this olefin was converted to diol under the conditions of Schaeffer's asymmetric dihydroxylation, and the resulting diol, diol was protected as cyclopentadiol acetal again. And the second alcohol was converted to the mesylate, and the benzyl group was selectively removed under the hydrogenous conditions with iron and nickel. Then this alcohol was treated with potassium carbonate in methanol. The intermolecular essence reaction occurred to give terminal epoxide with inversion of stereochemistry at C39, which were treated with this lithium reagent. The epoxide opening occurred here to give terminal alkyne. Then the secondary alcohol was protected as TBS ether. Then it could catalyze hydroalumination followed by iodination reported by Professor Hobader. The iodorephin 65 was obtained. Then removal of the PM group with DDQ and protection of the primary alcohol at TES ether to give the coupling partner compound 39. Then coupling reaction was carried out. The olefin were treated with tertiary butyllithium to generate alkyl lithium, which were treated with aldehydes to give the coupling product in 71% yield as a mixture of diastereomers at C43 and 1.7 to 1 ratio, which was produced as TBS ether. Then after removal of the test group, the resulting alcohol was oxidized to aldehyde, and this aldehyde was converted to the alkyne via alkylation by using the Aucher-Bestmann reagent in the process of cesium carbonate. And the resulting terminal alkyne was converted to this one by methylation with LHMDS and methyl iodide. Then palladium catalyzed hydrocyanidation was carried out, and the resulting stannum was converted to iodide by treatment with iodine to give the tri-substituted iod olefin. So now, having synthesized segments, we moved on to the final stage for total synthesis of M3. So after considerable experimentation, we found that the best conditions, as shown here, the hydroversion of the terminal olefin, and the point is to utilize 1 molar. The concentration is very important, 1 molar cesium carbonate, then addition of olefin, and then addition of palladium, tetrahydrophosphine palladium. As a result, the compound was obtained in 77% yield. So the coupling is very powerful. So the large molecule, large component, the molecular weight exceed around 2,000 can be combined to give the product. The molecular weight over 3,000 grams, very nicely. So then PMB group are removed, and then the resulting alcohol was oxidized to give aldehyde. Then Julia Koshansky refination by using this sulfone with KHMDS in the presence of HMPA. That is the compound obtained in 75% yield. The easy ratio is 10 to 1. The careful global deproduction of the side groups and cyclopentadiene ester was achieved by treatment with ethylpyridine and methanol and ethylene glycol. The compound obtained in 55% yield. The longest linear sequence is 40 steps, and the total number of steps is 112 steps. So the spectral data for synthetic specimen were in good agreement with those of the natural product, including the size and magnitude of specific rotation and antifungal activity, confirming the structure of M3 revised in 2008. The first total synthesis of M3 has been achieved, and revealing its true structure after more than 20 years since the first discovery. So the established method for total synthesis of M3 could be served as a general strategy for synthesizing not only other naturally occurring congeners, but also designed artificial analogs by changing the coupling partners corresponding to polymer moiety and polymer moiety via mirror coupling and Julia Koshansky refination in 5 steps. So based on the concept of minimum structure requirement, we expect that it would be possible to develop a simplified analog of M3 while retaining the antifungal activity. Focusing on the common structure among amphidiol congeners, we designed and synthesized a truncated analog corresponding to the C21 to C67 section of M3. As molecular weight is 955 by 28% reduction from M3, the natural product. So the antifungal activity, the MIC value, turned to be 20 microgram per disc, which is comparable to that of for M3, the natural product, 8 microgram per disc. So this is the first example of a biologically active artificial analog of MC possessing shorter polyol chain moiety. It is interesting to note that more truncated analog corresponding to the C31 to C67, this compound didn't show antifungal activity. So the C1 to C20 part, the polyol segment can be is not necessary for eliciting biological activity, but C21 to C30 part is very important to elicit the antifungal activity. Further structure activity relationship studies are in progress in our laboratory. So thank you for your kind attention.